charges repel and unlike charges attract. But here we are going to learn some more important properties of electric charge. So before that, listen. Here we are treating charges as point charges. So what about point charges? Last year we have learned about point objects. Point objects means, yes, if the size of an object is very small as compared to the distance, then that kind of object is considered as point objects. So like that, point charges means what? If the size of a charged body is very small compared to the distance, then that kind of charges are considered as point charges. Is it clear? Yes. So now we can discuss about the properties. So the first property is additivity of charges. Additivity of charges. Then second property, conservation of charge. Conservation of charge. And the third one, which is an important property, quantization of charge. Quantization of charge. Additivity of charges, conservation of charge, quantization of charge. Now we can discuss these properties in detail. So the first property is additivity of charge. So from the name itself, it is clear that charges can be added. Charges can be added. That is, if we have a system of charges Q1, Q2 and Q3, then what about the total charge of the system? Q1 plus Q2 plus Q3. We can add the charges. Or if we have a system of charges like Q1, Q2, Q3, etc., Qn. What about the total charge of the system? Q1 plus Q2 plus Q3 plus etc. plus Qn. So from this, it is clear that charges can be added like real numbers. Why? Because charges, these are all scalars. Why? Because charges are scalars like mass. But there is a difference between mass and charge. What is that? Yes, mass of a body, it will be always positive. But charges, of course we know that there are two types of charges, positive and negative. So charges can be positive or negative. So that means we have to consider this sign in the case of charges. So let's consider an example. If we have a system of charges plus 3 in any arbitrary unit, plus 3, minus 2 and minus 1. So what about the total charge of the system? Plus 3 minus 2 minus 1, that is equal to 3 minus 3 is equal to 0. So the total charge of the system will be 0 or the body is said to be neutral. So the thing is that in the case of charge, we have to consider its sign. Is it clear? Now let's move to the next property. The second property, what is that? Yes, conservation of charge. So the second property is conservation of charge. Conservation of charge. So last year we learned about conservation of energy, conservation of matter. So what about conservation of charge? Charges can neither be created nor be destroyed, but can only be transformed from one form to another form. Or in other words, in an isolated system, the total charge remains constant. The total charge remains constant. So what do you mean by isolated system? Isolated system is a system which never interacts with any other system. Is it clear? So what about the conservation of charge? In an isolated system, the total charge remains constant. So let's take an example, glass charge. So before we rub, glass rod is an isolated system. Silk cloth is an isolated system. So what about the charge of glass rod before rubbing? Yes, of course, neutral. What about silk cloth? Neutral. But the total charge is 0. But when we rub these two bodies, some amount of electrons are transferring from the glass rod. But the same amount of electrons are received by the silk cloth. So in this case, what about the total charge? Consider the system of this glass rod and silk cloth together. What about the total charge? The total charge is 0. That means there is no change for the total charge. Okay. So conservation of charge, I think now it is clear. Then one more thing. If charge is conserved or if some kind of energy is conserved means, what is the meaning of that? We can store such kind of energy. Of course, we know that we can store charges. Okay, so that is the physical significance of conservation of charge. So let's move to the next property. That is the third property, quantization of charge. Quantization of charge. So it is an important property. So listen carefully. Quantization of charge. So it is an experimentally proven fact that all charges are integral multiples of electronic charge. That is, charge on any body is the integral multiple of electronic charge. Mathematically, which is represented as Q is equal to Ne, where Q is the charge, N represents integers like 1, 2, 3, etc. and E is the electronic charge. E is the electronic charge. What about the charge of an electron? Charge of an electron is 1.602 into 10 raised to minus 19 coulomb. And by convention, we will take it as negative. Since electron possesses negative charge, it is minus 1.602 into 10 raised to minus 19 coulomb. So in the case of proton, this will be plus. Okay, so quantization of charge means the charge of any body is the integral multiple of electronic charge. And electronic charge is represented by E. So actually, what is the meaning of that? See, if I have a charge, let it be Q. Then this will be made of integral multiples of electronic charge. That means it will be made of 100 electrons or 200 electrons. And it can never be with 100.5 electrons or 200.5 electrons. So that is the idea. Is it clear? Now, what about the unit of charge? It is coulomb. And do you know one amazing fact? What are you thinking about 1 coulomb? See, don't be consider it as a silly thing because 1 coulomb, it is such a big unit of charge. Why? Because which is explained through an example problem in your textbook. That is, if 10 raised to 9 electrons are moving out of a body in every second, then it will take 198 years to get a charge of 1 coulomb. Listen, if 10 raised to 9 electrons are flowing out of a body or moving out of a body in every second, then it will take 198 years, that is around 200 years to get a charge of 1 coulomb. So 1 coulomb means it is a big unit of charge. It is too big. So that's why we have units like microcoulomb, millicoulomb, etc. And 1 microcoulomb is equal to 10 raised to minus 6 coulomb. And 1 millicoulomb is equal to 10 raised to minus 3 coulomb. So now we are going to do a problem. So here we have the problem. A polythene piece rubbed with wood is found to have a negative charge of 3 into 10 raised to minus 7 coulomb. Estimate the number of electrons transferred. So in this case, let me explain the problem. That means this polyethylene is having negative charge. So it is clear that electrons are transferred from wool to polythene. Is it clear? Electrons are transferred from wool to polythene. That's why polythene is negatively charged. Wool to polythene. And here we are going to calculate the number of electrons. So we have the equation from condensation principle, that is Q is equal to Ne. So the charge of the body is 3 into 10 raised to minus 7 coulomb. And what about E, electronic charge, that we already know. So from this we can calculate N, that is the number of electrons transferred. So Q is equal to 3 into 10 raised to minus 7 coulomb. Since it is negative minus 3 into 10 raised to minus 7 coulomb, then electronic charge E is equal to minus 1.602 into 10 raised to minus 90 coulomb. So what about N? N is equal to Q divided by E, that is equal to minus 3 into 10 raised to minus 7 divided by 1.602. We can take it as 1.6 minus 1.6 into 10 raised to minus 90. So what is the answer? It will be 1.8 into 10 raised to minus 7 plus minus 90, 10 raised to 12, or approximately 2 into 10 raised to 12. So in this case, the number of electrons transferred, that is 2 into 10 raised to 12. Is it clear? Now we are going to talk about the nature of force between 2-point charges. So consider 2-point charges Q1 and Q2, which is separated by a distance r. It is separated by a distance r. So what is the nature of force between these 2-point charges? It is given by Coulomb's law. It is given by Coulomb's law. So Coulomb's law states that the force between two stationary charges is directly proportional to the product of charges and inversely proportional to the square of the distance between them. Let me repeat. Coulomb's law states that the force between 2-point charges is directly proportional to the product of the charges and inversely proportional to the square of the distance between them. So in the next step, we can replace this proportionality sign by F is equal to a constant K into Q1, Q2 divided by R square. So last year, we have learned about the force of the same nature. Can you recall that? Yes, of course it is the gravitational force, or the Newton's universal law of gravitation. And Newton's universal law of gravitation states that in this universe, every particle attracts every other particle. And that force is given by F is equal to G m1 m2 divided by r square, where G is the gravitational constant, m1 m2 are the masses, r is the distance between them. But there is a difference between this gravitational force and the electrostatic force, or this force. What is that difference? Gravitational force, it will be always attractive in nature. But in this case, this force can be attractive or repulsive. That means, consider if I am taking two charges, positive and positive, charges of same type. So what about the nature of the force? Positive and positive like charges will repel. So this will be repulsive in nature. Now if I am taking another pair of charges like positive and negative. What about positive into negative? Negative. It will attract. So in this case, the force will be in attractive nature. Force will be attractive in nature. Is it clear? Okay. So this is the difference between gravitational force and electrostatic force. Gravitational force, which is always attractive in nature, but electrostatic force, this can epsilon 0. The value of K is 1 by 4 pi epsilon 0, where epsilon 0 is the permittivity of free space. Epsilon 0 is the permittivity of free space. And its value is, epsilon 0 is equal to 8.85 into 10 raised to minus 12. What about its unit? Listen, the value of K is 1 by 4 pi epsilon 0. So, F is equal to 1 by 4 pi epsilon 0 Q1 Q2 divided by R square. So, in order to calculate the unit of epsilon 0, from this equation, epsilon 0 is equal to 1 by 4 pi F Q1 Q2 divided by R square. So in this case 1 by 4 pi, it is a constant. What about the unit of F? Newton. So 1 by N. What about the unit of Q1? Since it is charge, Coulomb. Here also Coulomb. So Coulomb square divided by R square. What is the unit of distance? Meter. So what is the unit of R square? Meter square. Meter square. So from this, what about the unit of epsilon 0? 1 by N, that is Newton raised to minus 1 Coulomb square meter raised to minus 2. Meter raised to minus 2. Newton raised to minus 1 Coulomb square and meter raised to minus 2. Is it clear? Now this epsilon 0, that represents that how much nature is permitting the interaction, that is the interaction between two charges. How much nature is permitting the interaction between 2 point charges. That is epsilon 0. So epsilon 0 is the permittivity of free space. Permittivity of free space. And if it is a medium, means it is represented by simply epsilon. Here I am introducing another thing, that is epsilon r, which is known as relative permittivity. Relative permittivity means it is the ratio of permittivity of a medium to that of free space. Permittivity of a medium to that of free space. That is epsilon r is equal to epsilon by epsilon 0, and the relative permittivity of air is approximately equal to 1. So that is the idea about Coulomb's law. So what is Coulomb's law, or what about the electrostatic force? It is directly proportional to the product of charges and inversely proportional to the square of the distance between them. Now we are going to represent this Coulomb's law in vector form. Vector form of Coulomb's law. Listen, we have a charge Q1, another charge Q2 at a distance R. So what about the electrostatic force? F is equal to 1 by 4 pi epsilon 0 Q1 Q2 divided by R square. Since this force is a vector, we can represent it as F12 force, F12 vector F12, where F12 is the force on the first point charge due to the second. F is the force on the first charge due to the second. That is equal to 1 by 4 by epsilon 0 Q1 Q2 divided by R12 square. R12, this distance is R12. So R12 square. So here in LHS, F is a vector. So here also in RHS also we have to introduce some vector, and that is the unit vector R12. So this is the unit vector R12 along this direction. So this is the vector form of Coulomb's law, that is F12 is equal to 1 by 4 pi epsilon 0 Q1 Q2 divided by R12 square is the expression. Now if we are calculating F21, vector F21, that is the force on the second point charge due to the first, then it is seen to be equal and opposite to F12. That is F21 is equal and opposite to 1, 2. So this is in agreement with Newton's third law of motion. This is in agreement with Newton's third law of motion. Now the next thing, we are going to define 1 coulomb. 1 coulomb. So as I said earlier, 1 coulomb is such a big unit. So if I am saying 10 kg, 10 kilogram means you know how much it will be. But what about 1 coulomb? What are you thinking about that? How much it will be? 1 coulomb charge means how much it will be? Okay, let's examine that. Listen. 1 coulomb of charge. 1 coulomb of charge is that charge when placed at a distance of 1 meter from another charge of same magnitude in vacuum experiences a force of 9 into 10 raised to 9 Newton. Listen. We have F is equal to 1 by 4 pi epsilon 0 Q1 Q2 divided by R square. In this equation, if Q1 is 1 coulomb, Q2 is 1 coulomb, R is 1 meter. What about F? This will be 1, and what about F? F is equal to simply 1 by 4 pi epsilon 0. So here we have to substitute the value of epsilon 0. That is 8.85 into 10 raised to minus 12. So we will be getting the value of F 9 into 10 raised to 9 Newton. 9 into 10 raised to 9 Newton means after 9 zeros are there. So this value F is equal to 1 by 4 pi epsilon 0, that is 9 into 10 raised to 9 Newton. This you have to keep in your memory because we need this value for doing problems. Okay, so here we are going to do a problem. Yes, here is the question. What is the force between two small charged spheres having charges of 2 into 10 raised to minus 7 coulomb and 3 into 10 raised to minus 7 coulomb placed 30 centimeter apart in air? So here we have to find the force, and this force is given by Coulomb's law, that is F is equal to 1 by 4 pi epsilon 0 Q1 Q2 by R square. So what about Q1? Q1 is equal to 2 into 10 raised to minus 7 coulomb. What about Q2? Q2 is equal to 3 into 10 raised to minus 7 coulomb, and the distance R is equal to 30 centimeter, that is equal to 30 into 10 raised to minus 2 meter. We have to convert it into the standard unit. So 30 into 10 raised to minus 2 meter. So also we know that 1 by 4 pi epsilon 0, what is its value? 9 into 10 raised to 9. So here we are going to substitute. So F is equal to 9 into 10 raised to 9 into Q1, 2 into 10 raised to minus 7 into Q2, 3 into 10 raised to minus 7 divided by, what about R square? 30 into 10 raised to minus 2 whole square. So 9 into 2 into 3, that is 54 into 10 raised to minus 7, 10 raised to minus 14 into 10 raised to 9 divided by 30 square of 30. 900 into 10 raised to minus 4. So the answer will be 0.006 Newton or 6 into 10 raised to minus 3 Newton. So hope you have understood this problem. So this is for today. So in the next class we will come with a new topic. So if you have any doubt means once again go through the video or contact to my WhatsApp number. So we will meet you in the next video. Till then, bye.